think I'm live. So hi guys, this is Prasoon Varshney from Varshney channel. Today, actually, I was so late to stream because uh, there is a there was some work. That's why I can't able to stream on time. Today I got some haircut. As you clearly see my hairs here. Yeah, I miss my messy hairs. So yeah, without time wasting, I want to say that hey guys, uh, welcome to Study with SAP series. This is video number 24, I guess. Let me check. Yeah, this is video number 24. Video number 24 of consistency. Day number 24 of consistency. So yeah, we have a target of 3 sessions. Let us see if our OBS allows me to do so. I will do 3 sessions. So without time waste, let's start. I will study today microprocessors also. Okay, so let's start.
Hello people, I'm Bharat Acharya. Welcome to today's video. We're going to how to make timing diagrams in 8085. Now, timing diagrams is a topic that a lot of people have been requesting me to make this video because people find this topic tough. The point is, timing diagrams are probably the easiest things to draw. Yes, you may not agree with me at this point. If you don't know how to draw a timing diagram, it seems to be a humongous task. But just give yourself about 30-35 minutes to understand the first timing diagram. Once you understand the first timing diagram, after that you'll just realize it was so simple. You're just being scared of it for no reason. What do you do in a timing diagram? As the name suggests, it's a timing diagram. So you show the timing of signals. You draw timing diagrams of machine cycles. There are some fundamental machine cycles: memory read, memory write, IO write, and the big one, opcode fetch. First of all, you learn how to draw the timing diagrams of all these machine cycles. Once you know that, then you go on to learning how to draw timing diagrams of instructions, where you learn nothing new. An instruction requires several machine cycles. Every instruction will require an opcode fetch. That's the first machine cycle of every instruction. Thereafter, some instruction may require a memory read or a memory write or two memory reads or two memory writes or maybe two memory reads and two memory writes. What do you have to do? You have to draw opcode fetch and memory read and memory write and draw them together. So if you know how to draw these 5 basic machine cycles, thereafter you just have to draw them continuously in a sequence. There is nothing new to learn in that. You just have to figure out which machine cycle is required and draw it. So the whole understanding of timing diagrams is basically to understand how to draw the 5 fundamental machine cycles, for which also once you understand opcode fetch, you understand the others. The others are the changes are so minor. If you know one, you know all. I have drawn opcode fetch. I'm going to teach you how to draw this. Thereafter, memory read and memory write, I have purposely not drawn them. I'm going to draw them with you. We're going to draw it together. And you're going to be telling me what are the signals, which signals has to be made high, which has to be made low. And you'll yourself realize that everything you speak will be correct. Once you know one timing diagram, you know all. So, let's start. First thing you need to understand, what are machine cycles? Okay? A machine cycle is one data transfer in the system. Transferring one value of data anywhere in the computer is a machine cycle. You draw timing diagrams of machine cycles. Okay? Now, the 4 basic machine cycles. You know there are 3 parts in a computer. The MUP, that is the processor 8085, the memory and the IO. Memory devices means RAM, ROM, IO device means keyboard, mouse, printer, monitor, etc. Now, how can you transfer data in the system? Either you transfer data from memory to MUP, that's called a memory read cycle, or from MUP to memory, that's called a memory write. Similarly, IO read, similarly, IO write. So if I tell you define memory read for me, just define memory read. Transferring data from memory to the MUP is called memory read. Are you clear? How much data? 1 byte. You understand data will flow through the data bus. 8085 has an 8-bit data bus. That means in one machine cycle, you transfer 1 byte of data. Are you so far clear? So, in all these machine cycles, but just give yourself about 30-35 minutes to understand the first timing diagram. Once you understand the first timing diagram, after that you'll just realize it was so simple. You're just being scared of it for no reason. What do you do in a timing diagram? As the name suggests, it's a timing diagram. So you show the timing of signals. You draw timing diagrams of machine cycles. There are some fundamental machine cycles: memory read, memory write, IO write, and the big one, opcode fetch. First of all, you learn how to draw the timing diagrams of all these machine cycles. Once you know that, then you go on to learning how to draw timing diagrams of instructions, where you learn nothing new. An instruction requires several machine cycles. every instruction will require an opcode fetch. That's the first machine cycle of every instruction. Thereafter, some instruction may require a memory read or a memory write or two memory reads or two memory writes or maybe two memory reads and two memory writes. What do you have to do? You have to draw opcode fetch and memory read and memory write and draw them together. So if you know how to draw these 5 basic machine cycles, thereafter you just have to draw them continuously in a sequence. There is nothing new to learn in that. You just have to figure out which machine cycle is required and draw it. So the whole understanding of timing diagrams is basically to understand how to draw the 5 fundamental machine cycles, for which also once you understand opcode fetch, you understand the others. The others are the changes are so minor. If you know one, you know all. I have drawn opcode fetch. I'm going to teach you how to draw this. Thereafter, memory read and memory write, I have purposely not drawn them. I'm going to draw them with you. We're going to draw it together. And you're going to be telling me what are the signals, which signals has to be made high, which has to be made low. And you'll yourself realize that everything you speak will be correct. Once you know one timing diagram, you know all. So, let's start. First thing you need to understand, what are machine cycles? Okay? A machine cycle is one data transfer in the system. Transferring one value of data anywhere in the computer is a machine cycle. You draw timing diagrams of machine cycles. Okay? Now, the 4 basic machine cycles. You know there are 3 parts in a computer. The MUP, that is the processor 8085, the memory and the IO. Memory devices means RAM, ROM, IO device means keyboard, mouse, printer, monitor, etc. Now, how can you transfer data in the system? Either you transfer data from memory to MUP, that's called a memory read cycle, or from MUP to memory, that's called a memory write. Similarly, IO read, similarly, IO write. So if I tell you define memory read for me, just define memory read. Transferring data from memory to the MUP is called memory read. Are you clear? How much data? 1 byte. You understand data will flow through the data bus. 8085 has an 8-bit data bus. That means in one machine cycle, you transfer 1 byte of data. Are you so far clear? So, in all these machine cycles, 1 byte will be transferred. Now, when you draw timing diagrams, you are mainly showing these 5 signals. IO/M bar, read bar, write bar, S1, S0. In my architecture video, I have already explained these signals to you. No problem, we just go through it again. It's very simple. Ignore opcode fetch right now. Right now, don't talk nothing about opcode fetch. Memory read. For memory read, IO/M bar will be 0. IO/M bar indicates whether it's an IO operation or a memory operation. Memory read is a memory operation. So IO/M bar will be 0. 0 indicates memory, 1 indicates IO. I'm sure you will realize that. Memory write is also a memory operation, so 0. IO read and IO write are IO operations, so 1. So IO/M bar indicates whether it's a memory operation or whether it's an IO operation. Are you clear? Read bar and write bar, they both are bar, which means they are active low signals. So whichever is active, that signal will be 0, the other one will be 1. So, memory read is a read operation. So read bar will be 0, write bar will be 1, indicating that it's a read operation. Memory write is a write operation. Write operation, so write bar will be 0, read bar will be 1. Similarly, IO read, it's a read operation. So read bar will be 0, write bar will be 1. IO write is a write operation. Write bar will be 0, read bar will be 1. Please tell me, did you understand? Lastly, S1 and S0. For the sake of simplicity, we pronounce them as S input and S output. They are not. They are called S1, S0. They are called status signals. But if you want to simply understand them, they are pronounced as S input and S output. So, whenever we do an input operation, S input will be 1, S output will be 0. If we do an output operation, S output will be 1, S input will be 0. So basically S1 and S0 indicate whether you're doing an input operation or an output operation. The names input and output are given with respect to the MUP. For the MUP, memory read is an input operation. Do you understand? MUP is getting data. So since it's an input operation, S input will be 1, S output will be 0. Memory write is an output operation. S output will be 1, S input will be 0. Tell me, did you understand this? Now you answer yourself. IO read is an input operation. Since it's an input operation, S input will be 1, S output will be 0. IO write is an output operation. Output operation means S output will be 1, S input will be 0. Please tell me, did you understand this much? Now, if I tell you, tell me this row for one of the machine cycles, will you be able to answer? If you can answer for one machine cycle, you know it for all. Then you know the logic. Tell me, memory read. No cheating, don't try to look behind me. Let's not cheat over here, okay? Tell me clearly. Memory read. IO slash M bar will be 0 because it's a memory operation. Read bar will be 0 because it's a read operation. So write bar will be 1. Memory read is an input operation. So that means S input will be 1. S output will be 0. Please tell me, did you understand? If you know 1, you know all. Then it's the same logic, just the ones and zeros will change. The logic is the same. Now, since it's a timing diagram, you are also talking about time. All these machine cycles require time to be performed. Time in a processor is not given in terms of seconds or milliseconds or microseconds or nanoseconds, etc. Time is given in terms of T states, clock pulses. Every clock pulse is an input operation. So that means S input will be 1, S output will be 0. Please tell me, did you understand? If you know 1, you know all. Then it's the same logic, just the ones and zeros will change. The logic is the same. Now, since it's a timing diagram, you are also talking about time. All these machine cycles require time to be performed. Time in a processor is not given in terms of seconds or milliseconds or microseconds or nanoseconds, etc. Time is given in terms of T states, clock pulses. Every clock pulse is a trigger to the processor to do something new. So when we say how much time is required by these machine cycles, what we mean is how many triggers are required. That each clock pulse is called one T state. T stands for transition. Because on every clock pulse, there is a transition from one state to another state. As in, on every clock pulse, the processor does a new activity. Each clock pulse triggers a new activity in the system. So the system undergoes a transition from one state to another state to another state on every clock pulse. That's why one clock pulse is also called one T state. If you want to know how much is that duration, it is 1 upon the operating frequency. Operating frequency is 3 megahertz. 1 upon 3 megahertz. Mega's inverse is micro. 3's inverse is 0.3. So 0.333 microseconds or 333 nanoseconds. It's totally irrelevant in the topic. That's why I'm not even writing it on the board. I don't want to confuse you with unnecessary things. In case you wanted to know how much is a T state, it's 0.333 microseconds. Okay? Anyways, it's got nothing to do with what we are learning. So, coming back. All these machine cycles require 3 T states. It's standard, every machine cycle requires 3 T states. Now, what do you mean by 3 T states? 3 T states means 3 triggers. That means there are 3 small activities taking place in a machine cycle. It's not difficult to understand why 3 activities take place. It is so obvious. Suppose you think of memory read. What do you mean by memory read? And the MUP, this is memory. Memory read means the MUP is reading from memory. MUP is taking some data from memory. Now, are you reading from the whole memory or from one location? One location. That means first, MUP will have to give an address. Isn't it obvious? There's no rocket science in this. Data will not automatically come from the desired location. First, MUP will give an address. Now, when will it give an address? When the previous machine cycle was going on that time? No, that time it will give the address of that operation. Now that machine cycle is over. When the new machine cycle is going to start, MUP will give a new address. Tell me, do you understand? So here the previous machine cycle got over. Now MUP will give a new address. Once again, previous machine cycle got over. MUP is sleeping. Is that okay? No. Something happens. What do you mean by activities taking place in a machine cycle? It's not difficult to understand why 3 activities take place. It is so obvious. Suppose you think of memory read. What do you mean by memory read? And the MUP, this is memory. Memory read means the MUP is reading from memory. MUP is taking some data from memory. Now, are you reading from the whole memory or from one location? One location. That means first, MUP will have to give an address. Isn't it obvious? There's no rocket science in this. Data will not automatically come from the desired location. First, MUP will give an address. Now, when will it give an address? When the previous machine cycle was going on that time? No, that time it will give the address of that operation. Now that machine cycle is over. When the new machine cycle is going to start, MUP will give a new address. Tell me, do you understand? So here the previous machine cycle got over. Now MUP will give a new address. Once again, previous machine cycle got over. MUP is sleeping. Is that okay? No. Something has to trigger the MUP. Get this clear. MUP is not a human being. You and I, human beings, we are living objects. We understand time is passing. From now till now, time passed. We understand that. A MUP doesn't understand that. For the MUP, it's a dead object. For a MUP, time means triggers. Something triggers the MUP to do a new activity. So here the previous machine cycle got over. The first trigger will tell the MUP produce an address. That means on the first T state, MUP will release an address which will go out on the address bus. Are you understanding me so far? That address will go out on the address bus. Go to the memory, select one location. There are 64,000 locations, 65536, 64 KB memory. You know that, right? So out of 65,536 locations, one location will get selected. Will that take some time? Yes. How much time? Seconds? No. Nanoseconds. But then again, over here, everything is nanoseconds. What you're seeing over here is not activities over a second. These are all activities over microseconds and nanoseconds. Do you understand that? So that very small amount of time which is required for the location to be selected, it is so small that a human being will never notice it. But in this diagram, it will look like a big time because we are drawing everything in nanoseconds. Are you understanding my point? So again, first trigger, MUP gives address. That address goes to the memory, selects an appropriate location. Yes, it will take some time. Now, the location is selected. Now, on this location, two operations can happen. Either a read or a write. Who will decide that? MUP. By giving the appropriate control signal. Either read bar or a write bar. You tell me, we are discussing memory read. So that means MUP will give which signal? Read bar. Read bar, active low. So read bar has to go low. That means MUP has to do two things over here. First, give an address to select the location. Second, make read bar go low, asking for data. Tell me, do you understand low? Everything in nanoseconds. Are you understanding my point? So, again, first trigger, MUP gives address. That address goes to the memory, selects an appropriate location. Yes, it will take some time. Now, the location is selected. Now, on this location, two operations can happen. Either a read or a write. Who will decide that? MUP. By giving the appropriate control signal. Either read bar or a write bar. You tell me, we are discussing memory read. So that means MUP will give which signal? Read bar. Read bar, active low. So read bar has to go low. That means MUP has to do two things over here. First, give an address to select the location. Second, make read bar go low, asking for data. Tell me, do you understand this? Now my question is, should the MUP give the address and make read bar go low simultaneously? No. How can it be? By making read bar go low, MUP is asking for data. How can you ask for data if your location is still not selected? Remember I told you to select the location, it will take some time. Yes, it won't take seconds, it will take nanoseconds. Nanoseconds is a very small time in the real world, but in this diagram it's a very big time because you've zoomed in into nanoseconds to understand activities of the MUP. That means after giving address, MUP will have to wait for some time for the location to be selected. Tell me, are you with me so far? So MUP is waiting. While waiting, it falls asleep. Is that okay? No, MUP doesn't understand time. Time means you need another trigger. So the first T state tells the MUP to release an address. Second T state tells the MUP now give read signal. Please tell me, did you understand? The second trigger makes the MUP make read signal go low, read bar go low. So MUP makes read bar go low. That 0 travels to memory. Memory releases data. That data travels to MUP. Do you understand this? Will this traveling take some time? Of course it's going to take. We are not learning magic. MUP will make read bar go low and data will instantly come to the MUP. No, that's not going to happen. That read bar will travel to the memory. Memory will release data, will travel to the MUP. This time is called propagation delay, which you will be seeing on the board. I will show you. Anyway, so data started coming. MUP will see data is coming on the data bus. It is coming, data gone. Is that okay? No. MUP has to capture the data and store it into the appropriate register. Now, to do that also, will the MUP take some time? Yes. How much time? Infinite time? No. MUP doesn't understand time. Somebody has to trigger the MUP. That is the third T state. Finish. I've explained to you what a timing diagram is without even drawing one. In the first T state, the first trigger tells the MUP to release an address. The second trigger tells the MUP now give read signal so that we can start getting data. After some time data starts coming. The third trigger tells the MUP now capture the data and store it into the appropriate register. Do you understand why 3 T states are required in a machine cycle? Same goes with the read operation, same goes with the write operation. The only difference is in the write operation, MUP sends the data, but still the data has to travel and reach the memory, and the memory has to capture the data and store it. So it's still the same operation, same set of same sequence of operations. MUP will give the address, MUP will give the control signal, send the data, memory will capture the data. That's a write operation. So again 3 T states are required. Same goes with IO read, same goes with IO write. So in every machine cycle, do you understand why 3 T states are required? Now, before, I know you are eager now that you got this much, you want to start drawing a timing diagram. More than you, I am eager. This is one of the simplest topics to teach. But before I go there, one thing you need to know. Other than these 4 machine cycles, memory read, memory write, IO read, IO write, there is one major machine cycle which is there in every instruction called opcode fetch. I repeat, opcode fetch. Now the name itself gives its answer. Opcode fetch. What are you doing? Fetching the opcode. Tell me, is this optional or compulsory? Compulsory. Every instruction has an opcode. What do you do to every instruction? Tell me, what does the processor do to every instruction? Execute them. To execute them, first of all, processor has to fetch them. To fetch an instruction, first of all, processor will have to fetch its opcode. So the first machine cycle of every instruction is opcode fetch. Every timing diagram of every instruction you draw will begin with opcode fetch. Then, depending upon the simplicity or the complexity of the instruction, there may or may not be other machine cycles. But opcode fetch will always be there in every timing diagram. Please tell me, are you clear? Now, as the name suggests, opcode fetch. What are you fetching? Opcode. Opcode is a part of the instruction. Where are instructions stored? Memory. So opcode fetch is also an IO operation or a memory operation? Memory operation. You understand that? So memory operation means IO / M bar will be 0. Please tell me, do you understand? Opcode fetch is a write operation or a read operation? Read operation. So read bar will be 0, write bar will be 1. It's an output operation or input operation? For the MUP, it's an input operation. So S input will be 1, S output will be 0. But that's the problem. If S output is 0, then look at these 2 rows. They end up becoming the same. What does that mean? Opcode fetch and memory read end up becoming the same. Now, are they the same? No. They are very similar, but they are not the same. What are we talking about? Opcode fetch and memory read. Let's understand. In opcode fetch, you're fetching the opcode from memory to MUP. In memory read, you're getting data. I repeat, you're getting data from memory to the MUP. Both cases, you're getting how much information? 1 byte. So basically in opcode fetch and in memory read, you are transferring 1 byte from memory to the MUP. So that means they are almost the same, but there is a difference. In opcode fetch, you're getting the opcode. In memory read, you're getting ordinary data. Let's see what is the difference between the two. Suppose I have an instruction MBI B. MBI B, 25. Please tell me who gets what? B gets the value 25. Please tell me, are you clear? Now if B gets the value 25, this instruction, you understand, will have an opcode. I hope you've seen the addressing modes video. Please check out the video. In that I've explained this in more detail. So this instruction will have an opcode, no doubt. Will there be an opcode for MBI B, 25? Or will there be an opcode for MBI B? Of course, there will be an opcode only for MBI B. How can there be an opcode for MBI B, 25? 25 is the number. If numbers become part of an opcode, then it will be impossible to even have opcodes, because then there will be an opcode for MBI B, 25, another opcode for MBI B, 26, another opcode for MBI B, 27. Like this, there will be infinite opcodes. Tell me, did you understand this? So a number is never a part of an opcode. So the opcode of this instruction is for MBI B, and 25 is written as an operand. Operand means data. That means this instruction is a 2-byte instruction. 1 byte for the opcode, 1 byte for the operand. Tell me, did you understand this much? Let's say the opcode is 3E. Standard example, opcode can be any number. I'll take one such standard number 3E. If I keep changing in every example, you'll just be bothered about the number more than understanding the actual topic. So let's say the opcode is 3E. So there will be an opcode 3E for MBIB, and there will be 25, that is your data 25. This becomes a 2-byte instruction, so when stored in the memory, it will be stored in 2 locations. Tell me, do you understand? Out of the 2 locations, what should come first? The opcode or the operand? Obviously the opcode. Why? The opcode tells what to do with the operand. Operand doesn't tell what to do with itself. If MUPI gets the opcode first, it will understand what to do with the operand. If it gets the operand first, it won't understand anything at all. Tell me, do you understand this? So that's why the first byte of every instruction is the opcode. Now, come on, be with me. This was your instruction MBI B,25. MUPI has reached this instruction. It wants to fetch this instruction now. First of all, when I'm saying MUPI has reached this instruction, that means PC is now pointing over here. PC always gives the address of the next instruction. So you're doing some instruction that's over. PC is pointing over here. This is the instruction to be fetched. Please tell me, are you with me so far? So this is 2000, this is 2001. In other words, this is PC and this is PC plus 1. Tell me, do you understand? Now, we want to fetch this instruction. Being a 2-byte instruction, do you realize it will be fetched in 2 cycles? One cycle you can transfer only 1 byte. You require 2 cycles to transfer this instruction to the MUPI. Are you so far clear? Now, this cycle is called opcode fetch. This cycle is called memory read. Students say they both look the same to me. In both you are transferring 1 byte. What is the difference? I'm still not understanding. No problem. You're almost there. 1 minute and you'll know the difference between opcode fetch and memory read. Come on. When MUPI fetches 3E, 3E is the opcode. Try to remember the architecture. People, everything goes together. I'm sure you've seen the architecture video. This 3E will come into the architecture of 8085, will come into IR, instruction register. Yes, everybody clear? You've seen the architecture, right? From there, it will go to instruction decoder. Here the MUPI will, what? Give me the answer. What will the MUPI do? Decode the opcode. This is the key word. MUPI will decode the opcode. Will decode this opcode and understand 3E stands for MVIB. So who needs a value? B needs a value. This is when MUPI understands that 1 more byte is required in the instruction. The instruction is not complete. Are you clear? Students say, how does the MUPI know whether the instruction is 1 byte, 2 byte or 3 byte? By decoding the opcode. If the opcode was of move A, B, that opcode indicates everything. A will get the value of B. But here the opcode is MVIB. That's it. MVIB means there is 1 more data that is supposed to come. MVIB is just the first half of the instruction. So on decoding this, MUPI understands B has to get a value. MUPI will take the value 25 from the memory, put it inside B register. Now, this was fetched using opcode fetch. This number was obtained using memory read. If you've been paying attention, I hope you have. If you've been paying attention, tell me, what is the difference between opcode fetch and memory read? Both will transfer 1 byte from memory to the MUPI, no doubt. But in opcode fetch, you are getting the opcode. So the opcode also has to be decoded. In memory read, you're getting data. Data 25 is not decoded. Data 25 is directly put inside B register. Tell me, did you understand this? So basically, dash is equal to dash plus dash. Finish this and you understood it. Dash is equal to dash plus dash. Opcode fetch is the same as memory read plus decoding. In opcode fetch, you do everything that you do in memory read, plus you also have to decode the opcode. Please tell me, do you understand? So there are 2 things I want you to understand from this. First, are opcode fetch and memory read the same? No. Both are similar. Both will transfer 1 byte from memory, but opcode fetch also has to do decoding. Since they are not the same, first of all, they cannot have the same set of signals. Otherwise, we'll never come to know which machine cycle is going on. So to differentiate between an opcode fetch and memory read, opcode fetch, in opcode fetch, S1 and S0, both of them are kept as 1, 1. What did I tell you? S1 and S0 are not S input, S output. For the sake of convenience, we treat them as S input, S output. They are basically status signals. They are 0, 1. They are 0, 1 for any write kind of operation. They are 1, 0 for any read kind of operation. And they are 1, 1 to indicate that we are doing opcode fetch. Please tell me, did you understand this? Is the role of S1 and S0 clear? Did you understand why S1 and S0 are 1, 1 for opcode fetch? Now, question about T states. All machine cycles require how many T states? 3. What are the 3 T states? Tell me once again. First T state, give the address. Second T state, give the read signal. Third T state, get the data. So every machine cycle requires how many T states? 3. Opcode fetch requires 4 T states. Please tell me, did you understand why? Please tell me, I want the answer from you. What is that 4th T state for? Exactly, for decoding. First 3 T states will be the same as memory read. Like memory read, you will get 1 byte inside the processor. But in the 4th T state, you will also decode. You understand, decoding cannot happen before the fetching, cannot happen during the opcode being fetched, because till the time it's not being fetched, how do you decode it? Once the 3 T states are over and the opcode has come inside the MUPI takes one more T state to decode the opcode. This is why opcode fetch 4 T states and other machine cycles of 3 T states. Please tell me, did you understand? And some instructions which are a little more complex in nature have a 60 state opcode fetch. That is very rare. There are totally 8 instructions in the whole instruction set having a 60 state opcode fetch. When you learn them, you'll also understand why they are. If you want a simple hint, I will tell you right now, whenever there is a 16-bit operation performed during opcode fetch is of 60 states. Right now, don't think of that. You don't learn exception first. This is why people think some topics are difficult. They try to understand the most exceptional case first. First, understand the rule. 66 out of the whole instruction set of 74 have a 40 state opcode fetch. Only handful of instructions have a 60 state opcode fetch. First understand the 40 opcode fetch. You will understand the 60 also when the right time is there. First, did you understand why opcode fetches of 4 T states and other machine cycles are of 3 T states? Tell me, what is that extra T state used for? Decoding. Which T state will do the decoding? First T state, second, third or fourth? Fourth. Because the first 3 T states, first you have to get the opcode and the 4 T state decoding will happen. Please tell me, is this clear? Now that you understood this table, you are on the verge of understanding a timing diagram. But again, just one thing you need to know. Patience. Patience is very big virtue. If you have it, you go places. Before we start drawing the timing diagram, you need to understand what is address data demultiplexing. This is a separate question by itself and is also useful in every interface, but more than that, if you don't know what this is, you will never understand a timing diagram. You can by heart it, but you'll never understand it. Okay? So just give me a minute. It will take only a minute. It's very simple. You know, MUPI has a 16-bit address bus, A15 to A0. I'm dividing it into two halves, A0 to A7, A8 to A15. This is lower 8 bits, this is higher 8 bits. This is called lower order address bus, this is called higher order address bus. LOMA, HOMA. Now, what is the size of the data bus? 8 bits. D7 to D0. Now, these are 8, 8 and 8. 24 pins. If left by themselves, they will occupy 24 pins on the MUPI. MUPI is a 40 pin IC, out of which 24 will be these only. The idea they've used is, these two buses are multiplexed together as a common bus, AD7 to AD0. This bus is A15 to A8, as in this bus will either carry address or carry data. Do you ever give address and data both together? No. First you give address, then you give data. Since first you give address and then you give data, why give it on two buses? Give it on the same bus, you will reduce the number of pins. That is called multiplexing. I've explained it in detail in the architecture lecture. Right now I'm not explaining multiplexing. Okay? I'm just telling I need this to make you understand something, to make you understand timing diagram. So I'm just using this part which I've explained earlier. So this is a bus which can either carry address or it can carry data. This bus always carries address. Are you clear? Since this bus always carries address, you are not bothered about this. Whenever you look at this bus, it will always carry address. But if you look at this bus, it may carry address, it may carry data. How do you know whether it's carrying address or data? ALE. There is a signal called ALE. The full form of ALE is address latch enable. I repeat, address latch enable. Within 1 minute you will understand this full form. Within 1 minute. Okay, right now just know the full form, address latch enable. So ALE can be 1 or 0. If ALE is 1, the bus is carrying address. If ALE is 0, the bus is carrying data. So after today, whenever you look at this bus, you also keep an eye on ALE. If ALE is 1, the value on this bus is address. If ALE is 0, the value on this bus is data. This bus has nothing to do with ALE, will always carry address. Please tell me, do you understand this? Look here. Now same thing I'm showing you over here. Look here. This is your MUPI 8085. This is the address data bus. So this bus carries address also, this bus carries data also. This is the higher order address bus which only carries address. Are you clear? So since this only carries address, there is no issue. This is the bus that carries both address and data. What we need to do now is separate out address and data. That means multiplex them or demultiplex them. Demultiplex them. Students say, what nonsense? If we had to demultiplex them, then why did we multiplex them in the first place? Why did we multiplex them? To reduce the number of lines. So that from the MUPI, I am the MUPI, from the MUPI, address and data both should come out on the same bus so that we reduce the number of pins. But once they are out of the MUP, when they come into the circuit, you need separate buses for carrying address and data, because address has a different role to play, data has a different role to play. Please tell me, do you understand? Look here, look here, look here, look here, look here, look here. In this classroom, there is a door. Come on, look here. Now, from this door, hundreds of people come. Now, for all the hundreds of people, I am not going to have hundreds of doors. There is one door through which everybody passes one by one. Think of two people coming in as address and data. They come in one by one from the same door. So, what is the advantage of coming one by one? You have one door. You reduce the hardware. This is the MUP. Thing behind me is the MUP. From the MUP, address and data come out on the same bus. But once they are there in the circuit, they are not together. Then they will sit in their own separate location. You understand my point, right? Once they are out of the MUP, this is address, this is data. You multiplex them so that on the MUP there are less spins. Once they are out of the MUP, on the circuit you need a separate address bus and a separate data bus. So that demultiplexing, separation of address and data is what is happening over here. This is a bus 80 to 87. This will carry address as well as data. This bus is given to a device called a latch. There are various chip numbers 74373, 8282, 8283, etc. There are different companies manufacturing different latches. Whichever number your college textbook is using, immaterial. If you're using the standard textbooks, then it is 74373. It's an 8-bit latch. The point is it's a latch. What does the latch do? This is a bus. If there is no latch, whatever comes on this bus will go. You send 25, 25 will go from here. 2 minutes later, if you look at the bus, it won't carry 25. A bus is used to transfer value, not store a value. But if you put a latch on the bus, now you send 25, the value 25 will go out from here but is also being latched. Even if you stop sending 25, the latch will continue to produce the value 25. It will hold the value. Latch is a set of D flip-flops. A flip-flop is used to hold a bit. 8-bit latch means 8 flip-flops, they can hold an 8-bit information. Now look here. To this latch we give this signal called ALE. ALE stands for address latch enabled. Didn't I tell you within 1 minute you understand the full form? Address latch enabled. ALE goes to this pin called gate. Now everything will become crystal clear. Initially ALE is 1. At that time bus carries address. That address is captured by the latch. Latch produces address. Why did address enter? Because ALE is 1. ALE goes to gate. When gate is 1, the gate of the latch is open. Entry is allowed into the latch. After some time, ALE will become 0. This bus will start carrying data. Data will also try to enter the latch, but because ALE is 0, 0 goes to gate, the gate is shut. Data will try to enter but cannot enter. Data will come out from here. So this becomes data. This bus, this latch, initially had captured address the same way because it is a latch, it can store. So whatever was coming earlier that was captured over here, that address will now come out over here. Please tell me, do you understand this? Let's take with simple examples. Come on. ALE is 1. This bus carries a value A. Will A enter the latch? Yes, because G is 1, the gate is open, A comes here, A comes out over here. Are you clear? Now, ALE becomes 0. The bus contains a value D. Will D enter the latch? No. What will come out from here? D. What will still come out from here? A. Because who is giving that A now? The latch. We have stopped sending it, but the latch is giving it. So this is how we separated address and data. This bus carried two things, address and data. Initially when ALE was 1, the bus carried address, that goes into the latch. Latch produces address. Now when ALE becomes 0, the bus carries data. Data cannot enter the latch because gate is shut now. Data will come out from here, address will come out from here. So what we have done is we have separated out address and data. Imagine this is a bus that was carrying address and data. When it was carrying address, ALE was 1. I am the latch. Because ALE is 1, my gate is open. I capture the address. Now I say, I will produce address. You as a bus are free to carry data. So now the bus will carry data, the latch will produce the address. Please tell me, did you understand? So this was a bus carrying address and data. Produce address from here, A. Because who is giving that A now? The latch. We have stopped sending it, but the latch is giving it. So this is how we separated address and data. This bus carried two things, address and data. Initially when ALE was 1, the bus carried address, that goes into the latch. Latch produces address. Now when ALE becomes 0, the bus carries data. Data cannot enter the latch because gate is shut now. Data will come out from here, address will come out from here. So what we have done is we have separated out address and data. Imagine this is a bus that was carrying address and data. When it was carrying address, ALE was 1. I am the latch. Because ALE is 1, my gate is open. I capture the address. Now I say, I will produce address. You as a bus are free to carry data. So now the bus will carry data, the latch will produce the address. Please tell me, did you understand? So this was a bus carrying address and data. This is a bus that will only carry address. Are you clear? We have separated out address and data. So this was AD0 to AD7. This becomes A0 to A7. This becomes D0 to D7. And this higher part is A8 to A15. It does not require any latch because it always carries address. So this finally becomes your address bus. This becomes your data bus. ALE is called ALE because, come on, give me the reason. It enables the latching of address. Hence the name address latch enable. Please tell me, are you clear? Now, with that knowledge in our background, I promise you, 5 minutes from now, all that fear that you had of timing diagrams will just wipe out. Okay? Look here. Promise. We start drawing the timing diagram of opcode fetch. Opcode fetch is of 4 T states. First 3 T states for fetching, the 4th T state for decoding. Everybody knows this? Now these are the signals that you show in a timing diagram. Starting with the first one, clock. It's the easiest signal. What are these? T states. What is a T state? 1 clock pulse. So if there are 4 T states, there will be 4 clock pulses. Can you see? And you know from architecture lecture, 8085 works on pin diagram lecture, sorry. 8085 works on 3 megahertz at 50% duty cycle. So the clock should look like 50% duty cycle, which means half time low, half time high. Of course, no examiner is going to take a scale and measure. It should fairly look like half time, half time. Is it looking like half and half to you? As long as it's looking half and half, you're right. Okay? Now, this is the part that I explained to you over here. A15 to A8, AD7 to AD0 and ALE. Come on, look here. A15 to A8, AD7 to AD0 and ALE. What do you know? This is your multiplex bus. Multiplex bus means it can carry both address and data. Here, before T1, some other machine cycle was going on. That is over. Now new machine cycle has started. The bus will start, both the buses will start carrying address. What did I tell you? First T state, mu P gives an address. So both buses will give address. A15 to A8 will have the higher order memory address, which means basically the higher byte of PC, PCH. Are you clear? If the address was 2000, this will be 20. This will be 00, lower byte of the address. Now, this bus is not multiplex. It will always carry address. This is a multiplex bus. It will carry address for some time as well as data for some time. Initially, it will carry address. When it is carrying address, the latch should capture the address. Who tells the latch that the bus is carrying address? ALE. That is why when the bus is carrying address, ALE is 1. Address latch enable. This 1 enables the latching of the address. This address is now captured by the latch. Now the bus is free to carry data. So the lower order address is only for 1 T state. The higher order address is for 3 T states. Student says, sir, how is this possible? Half your address is there for the whole time, half your address is there only for little time. Please no, this is only for 1 T state in the bus. The latch will give the address for all the 3 T states. Come on, look here, look here, look here. This is the higher order bus. It will carry address for all the 3 T states. This is the lower order bus. It will carry address only for 1 T state. That doesn't mean the lower address is there only for 1 T state. When this was carrying address, the address came inside and came out from this latch. For the remaining 2 T states, this bus will carry data, but the latch will produce that lower order address for the remaining 2 T states. So this bus was initially carrying address, then was carrying data. This was initially carrying address, then was carrying address. That means for all the 3 T states, this bus will give address. That means your full address, higher order as well as lower order, full address is available for all the 3 T states. Don't look at this and think the lower order address is only for 1 T state. It is only for 1 T state on the bus, but on the latch it is there for all the 3 T states. Please tell me, did you understand this? Now, so I'll repeat this part again. ALE is 1. Every timing diagram begins with ALE. Okay, follow the lead of ALE and everything will become clear. ALE is 1 always for the first T state. First T state, ALE is gone. Done. Now, when ALE is 1, both buses will carry address. The higher bus has nothing to do with ALE, it will always carry address. The lower bus will carry address because ALE is 1. ALE becomes 0, the bus shuts down. Address is over. It has been captured by whom? Come on, address is captured by whom? Latch. Latch will give the address. The bus is free to carry the data. What timing diagram are we learning? Opcode fetch. That means it's a write operation or it's a read operation? Read operation. Data has to come from where? Memory. Will that data take some time to come? Yes. That time is called propagation delay. Can you see this dotted region over here, half a T state? That is called propagation delay. If you don't show it, you don't get marks. If you show data directly from here, you lose marks. Remember, my friend, what is this? It's a timing diagram. What is important? Timing. If timing is wrong, no matter how beautiful your diagram is, you won't get marks. It's the timing that gives you marks. Data cannot come immediately because it is coming from memory. It is going to take time to travel. Yeah, what will it take? Seconds? No, it will take nanoseconds. All this is nanoseconds. A T state is 0.33 microseconds. That means 333 nanoseconds. This duration is barely 100 nanoseconds. It's all nanoseconds, but it's still a time which has to be shown in the diagram. Please tell me, did you understand this? So for this much time, there is a hold period for after which data will start coming from the memory. This data is captured by the MUP by the end of the third T state. By the time 3D states are over, your opcode fetch is over. Fetching of the opcode is over. What happens after that? Decoding. Where does decoding happen? On the bus or in the MUP?
So hi guys, one session is over. I think there are one session is over. We can write. Let me check if there are some command. Okay, first we switch off this timer and add take time because who doesn't leave love break? Everyone love breaks, break up. Yeah. सारी गाली मैं क्यों सुना रहे हो? सुधा वार्ष्णेय ने कब कमेंट कर दिया? अच्छा, ओके, वॉइस कम कर ली जाए. Okay, sorry, bro. Sorry, bro. Sorry, mom. Sorry, so sorry. बट तुम आके भी बोल सकते थे ब्रो. चल मैंने आवाज़ कम कर दी है. नो प्रॉब्लम. And lower my music. Okay. Good proceed. Okay. I think I don't need break now. I think I don't need break. I will continue a session also. That kill this break time. My break is over. As there is no person to talk with, I think you know my what the fuck. I'm telling you this. It uses 92% of my CPU and 92%, 70%. Basically, OBS is using lots of memory. 83% of memory being used after me.